For just 1 minute. Okay. So any doubt from last class, Ifra?
No, sir.
Okay. So in last class, we have completed how to solve calorimetry part or heat exchange. Next is transfer of heat. Or simply heat transfer. We mainly have three different types of transfer of heat. First is conduction. Second is convection. And third is radiation. Conduction is transfer of heat through any solid material. Convection is heating of fluid. And radiation, if there is no requirement of any medium, further propagation, just like electromagnetic wave, is called radiation. So this second part, convection, is deleted from your syllabus. So we're left with only two parts, that is conduction and radiation. So first is how to define transfer through conduction method, or what do you mean by simply conduction? Suppose you have any solid. So it will have particle placed at their lattice point like this. Still, they will have some minimum separation in between them. Now, if you supply heat to any one end, it will causes to increase their vibrational energy. So initially, they were vibrating up to this point only. Now, on applying heat to this end, vibrational energy increases or kinetic energy due to temperature increases. So they will tend to vibrate some longer distances. During this process, they may collide elastically with their neighboring particle, during which they may transfer some of their energy to them. This transfer of energy will take place from one end to other end till flow of heat from one end to other end. So this is the entire process taking place for this particular conduction of heat from one end to another end. Ifra, is it clear?
Yes, sir. Yes, it is clear.
So we can say for this conduction part, on supplying heat at one end, kinetic energy, thermal, or simply thermal kinetic energy of particle increases. So they will tend to vibrate to larger distance, during which they may collide with neighboring particle and transfer their energy. This process continues till energy from one end get transferred to other end. Now, to define this more clearly, let me give you example of electricity. So first write it down, then I'm defining this part with respect to electricity.
Done, sir.
Okay. So in left hand side, we have electric current. And right hand side, heat current, or simply conduction of heat. Suppose you have any solid having area of cross section from this point to this point A, and length of this particular conductor L. So to flow electric current or charge through it, we must need any external agency to create potential difference across it. It means we should require some potential difference across its end to flow charge through this particular conductor. So first, potential difference. Delta V equals to V1 minus V2. Similarly, for flow of heat from one end to other end, let's say area of cross section A and length L. We should require some temperature difference across its end. Let's say this end having temperature T1 and this end having temperature T2. So for flow of heat, we must require some temperature difference. Delta T equals to T1 minus T2. Ifra, is it clear?
Yes, sir.
Now, every object having some opposition to the flow of particle through it, like for electric current or the flow of electric charge through it, it must offer some opposition, which is called a resistance. So next is electrical resistance, which is equals to rho L by A, where rho is called resistivity, L is length of conductor, and A is area of cross section. We may write rho is equals to 1 by sigma, where rho is resistivity. So sigma is called conductivity or electrical conductivity. Similarly, in terms of heat, we may define thermal conductivity related to the sigma, which is in electricity. So resistance offered due to this flow of temperature heat in this part will be thermal resistance, which is equals to rho, but in this part it will be 1 over K times L by A. Ifra, is it clear?
Yes, sir.
So K in this part is thermal conductivity. Now, you must have learned about Ohm's law.
Yes, sir.
So first, in this part for electric current, current equals to rate of flow of charge. So it will be charge flowing per unit time. So Q in this part is charge flowing per unit time is called electric current. Similarly, for heat or flow of heat, we may define heat current. This is called electric current, and this is called heat current. Current simply means motion through any particular medium. So if it is motion of electric charges, that is called electric current. Motion of heat, it will be termed as heat current. Motion of water, water current. Motion of air, air current, and so on. So heat current is flow of heat through any conductor per unit time. So Q in this part is heat flowing. Is it clear?
Yes, sir.
Now, we have to relate these different quantity according to Ohm's law. So we can say, according to Ohm's law, the amount of current flowing through any conductor should be directly proportional to potential difference across it. So the more the potential difference applied, the more amount of current would flow through it. So you can say potential difference and current should be directly proportional to each other. So according to it, potential difference equals to resistance times current. So we have to calculate current. So current equals to potential difference divided by resistance. We may write current as flow of electric charge per unit time. In terms of this voltage, it will be A times delta V divided by rho times L. Similarly, we may define Ohm's law in terms of heat current as H is equals to flow of heat per unit time, which is equals to temperature difference by thermal resistance, and which is equals to Ka delta T divided by. So if you remember this particular relation like this, it will be easy for you. Ifra, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Now let me give you a question related to this part. Suppose you have a rod this end is connected to furnace at 100 degrees Celsius. This end connected to ice at 0 degrees Celsius. Length of this particular rod is 0.5 meter. Length and breadth is 10 centimeter and 10 centimeter each. Thermal conductivity is 0.8 watt per meter square per Kelvin. So from this part, we have to calculate find first temperature difference, second temperature gradient, third thermal resistance, fourth heat current, fifth heat reached at ice end in 1 minute, and with this much amount of heat, amount of ice melted. Amount of ice melted using this heat. Try to find this part.
Okay, sir.
Ifra, any doubt while solving?
No, sir. Sending.
Okay. Since we have done, since you have calculated heat reached at other end, so this heat will be responsible to melt some of ice. So Q equals to mass of ice to be melted times latent diffusion. Mass equals to Q reached at other end, that is heat into time taken. Just equate these two terms and try to find mass of ice melted. In this part, latent fusion constant for ice is 80 calorie per gram. So we have to convert it into joule. So 1 calorie is equals to 4.2 per gram 10 to the power minus 3. Just put this in this part, you'll get mass of ice melted during this.
Okay, sir.
Good. You may say it 0.5 gram. Okay.
Okay, sir.
Next, you'll be asked to find temperature of junction. Suppose we have a rod, this, another rod, this. This is connected to 100 degrees Celsius, and this is at 0 degrees Celsius. Length of this rod is 0.5 meter from this point to this point, and length of this rod is 0.4 meter. Thermal conductivity of this rod is 0.8 watt per meter square per Kelvin. I think it would be per meter only. Next, thermal conductivity of this rod is 0.2 watt per meter per Kelvin. So for this combination, we have to calculate temperature of junction. Find temperature of junction. So you'll say we have 100 degrees Celsius higher temperature, so heat current will flow across this. Let's say temperature of this junction is T0. So we may define heat current in first part as Ka divided by length times temperature difference 100 minus T0. Similarly, heat current in this rod H2 equals to Ka divided by length temperature difference T0 minus 0. Let's say area of cross section of this rod is twice as compared to this rod. Just put these two values And since this particular combination is in series, so we can say in series combination, H1 and H2 must be equal to each other. Is it clear?
Yes,
Not.
sir.
I think answer would be like this. Ifra, you got this or something else?
Sir, sir, it was same right now. I was just going to divide 320 by 3.7. Means
Okay, okay.
I was at last step first.
Got the same result?
Yes, sir.
Okay. Now, next problem is calculation of rod in series and parallel combination. Before that, let me define you concept of Kirchoff's law of electricity, or simply Kirchoff's current law. Suppose you have a junction like this connected by 4 different roads. Now, along this path, suppose 4 individuals are coming towards this. Along this path, 5 individuals are coming. And along this path, only 3 individuals have gone. So how many individuals must follow this particular path if there is no accumulation of any individual at this particular junction? Ifra,
Yes, sir.
what will be our answer? We have 4 individuals coming along this way
Sir,
and 5 individuals coming along this way. So total individual reaching to this end will be,
9.
and only 3 have moved along this way. So how many individuals moved along this way? 9 minus 3. So you're left with 6. Okay.
Yes, sir.
Similarly, like this, current also behaves. So state, if there is no accumulation of charge at the junction, so sum of all current at the junction must equals to 0, or you will say total inward current must equals to total outward current. So it is based on conservation of charge. State, if there is no accumulation of charge at junction, then the algebraic sum of all current at junction should be 0. Sum of all current must equals to 0, or you can say sum of all inward current must equals to sum of all outward current. You may use sign convention. Take outward current to be positive and inward current to be negative, then you'll get this particular result. Ifra, is it clear?
Yes, sir. Yes, sir.
So, related to this concept, you'll be asked another question. Suppose we have a rod, this, another rod, this, and another rod, this. If rods are identical, let's say temperature of this particular junction is 0 degrees Celsius, this junction is 30 degrees Celsius, and this junction is 90 degrees Celsius. If the rods are identical, find temperature of junction. So how to calculate? Let me define you. First, just consider, let the temperature of this particular junction is X. And I'm just assuming total current must be outward along each different rod. So in this part, let's say heat current is H1. And this part, let's say heat current is H2. And this part, let's say heat current is H3. So according to formula, H equals to Ka divided by length times temperature difference X minus 0. In second part, H2 equals to Ka by L, temperature difference X minus 30. And third part, H3 equals to Ka by L, temperature difference X minus 90. Ifra, is it clear?
Yes, sir.
First, write it down to this part.
Done, sir.
Now, according to the above rule, Kirchoff's law of current, since I've just assumed total current to be outward, and outward current must be taken as positive. So sum of all current at the junction must equals to 0. So H1, H2, H3 must equals to 0, in which Ka divided by L, take it as common. So you're left with X minus 0, then X minus 30, and then X minus 90 equals to 0. This coefficient part moving to other side becomes 0. So X plus X plus X, we have 3X equals to 30 and 90, it will be 120. It means X is equals to 40 degrees Celsius. Is it clear?
Yes, sir.
Now put this value in the above expression. So if you put in this first part, you will get 40 times Ka by L. In the second part, you will get 10 Ka by L. But in third part, it will be minus of 50 Ka by L. If your answer is coming out to be positive, it means your assumption is correct. But if it is coming to be negative, then just reverse the direction of current. It will give the same result. It means H3 we are getting negative value. It means it must be towards inward, and H1 and H2 must be outward. So that total inward current must equals to total outward current. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Any doubt?
No, sir.
So this is how we can calculate temperature of junction related to any combination. Next, we have to calculate combination of rod in series and parallel. So next is combination of rod. First is series combination. Suppose this is first rod, second rod, having different length, but same area of cross section. An equivalent rod of this hole let's say this. This is first one, having thermal conductivity K1 and length L1 from this point to this point. This is the second one, having thermal conductivity K2 and length L2. Let's say temperature of this end is T1 and temperature of this end is T2 and temperature of junction is T0. Now on combining these two rods together, the equivalent becomes this K equivalent, and total length of rod from this point to this point is L1 plus L2. So temperature of this end is T1 and this end is T2. Area of cross section A and A. So this is equivalent part of the above combination. Ifra, is it clear? Okay. Now we have to combine these two different terms. So first, heat current through first rod. According to the formula, H equals to K A divided by length, temperature difference T1 minus T0. That is in first part along this way. So we may write T1 minus T0 equals to H L divided by K in A. Let's say this is equation first. Similarly, heat current through second rod. So it will be H equals to K A divided by length times temperature difference T0 minus T2. That is from higher temperature towards lower temperature. So we may write T0 minus T2 equals to H L divided by K into A. Let's say this is equation 2. Now on adding these two parts, on adding equation first and second, we have in left hand side T1 minus T0 for first part and T0 minus T2 for second part, which is equals to HL by K into A plus HL by K into A. So T0 and T0 will cancel out. So you're left with T1 minus T2 equals to HL by K into A and HL by K into A. Let's say this is equation third. Is it clear, Ifra?
Yes, sir.
Okay, just write it down up to this part. Now, from the equivalent part, for equivalent rod, H equivalent equals to K equivalent times area, total length L1 plus L2 times temperature difference T1 minus T2. So we may write T1 minus T2 equals to H equivalent multiplied by L1 plus L2 divided by K equivalent into A. Let's say this is equation fourth. Ifra, is it clear?
Yes.
Now, since this combination is series, so we can say in series combination, heat current or simply current will be same. So for series combination, H1 equals to H2 equals to H equivalent. So from equation 3 and equation 4, we may write, since both having same term in left hand side, so I can equate them. H multiplied by L1 plus L2 divided by K equivalent into A equals to H L divided by K into A plus H L divided by K into A. H by A, H by A, H by A becomes cancel out. So you're left with L1 plus L2 divided by K equivalent L1 over K1 and L2 over K2. So this is your final expression of getting K equivalent for series combination of rod. Efra, any doubt? Okay, just write it down. Similarly, we have to calculate for parallel combination. So next is parallel combination. This is first rod. And this is second one. And this is their equivalent part. This is first rod having thermal conductivity K1. Second rod having thermal conductivity K2. Both end connected to same temperature, let's say T1 and T2. Area of cross section of this rod is A1. This rod is A2, and both having same length L. So on combining these two rods, equivalent of this will become this. K equivalent, length L. Area of cross section from this end to this end becomes A1 plus A2. Temperature of this end is T1 and temperature of this end is T2. So we have to relate these two different terms. So first is heat current through first rod. According to the formula, H is equals to Ka by length times temperature difference T1 minus T2. Let's say this is equation first. Next, similarly, heat current through second rod, H2 equals to Ka A by length, temperature difference T1 minus T2. Let's say this is equation 2. On combining these two parts, H equivalent and for equivalent rod, H equivalent equals to K equivalent times area of cross section, temperature difference divided by length. Let's say this is equation 3rd. Ifra, any doubt?
No, sir.
Now, according to combination, suppose you have a wire which may divide into two parts so that there is a resistance at this point and there is another resistance at this point. So we may join like this. So if current through this particular wire is I, so at this junction, it may divide into two parts. There will be some current along this way, H1, I1, and some current along this way, along resistance R1 and R2 respectively. So we can say in parallel combination, current simply divides into number of division according to resistance offered, or total inward current must equals to total outward current. Similarly, in this part, we have heat current across this first rod H1 and across this second rod H2. So combination will must have total current H1 plus H2. Is it clear?
Yes, sir.
So according to this concept, we can say as in parallel, H equivalent must equals to H1 plus H2. Now put their values according to equation 1st, 2nd, and 3rd. So for H equivalent, we have K equivalent A1, A2 times T1 minus T2 divided by length equals to H1 K A T1 minus T2 by length L and K A temperature difference T1 minus T2 by length L. So we have T1 minus T2 divided by L common in all of these different parts. So on combining, you may write K equivalent equals to K1 E1, K2 A2 divided by A1 plus A2. So this is your final thermal conductivity in the parallel combination. Ifra, any doubt?
Yes, sir. No, sir.
Okay, just write it down. Now, related to this part, there will be some question. Suppose we have one of the rod is along this way, another rod like this. Now, for this arrangement, suppose we have three identical rods, but different thermal conductivity. This is 3K, 6K, and 2K. If temperature of this particular junction and this particular junction, these are connected at two different temperatures, let's say T1 and T2. So we have to calculate, find K equivalent for this particular combination. So first, how to define which of these different rod must be in series and parallel. So start from any one end of temperature. Let's say from T1. So there will be heat current along this way. Let's say H. Since at this point there is junction, so there will be division of current along this path and along this path. So let's say H1 will belong this way and H2 will belong this path. H1 on reaching to this end, since there is no any further division, there is only bending of path. So H1 will remain H1. Now on reaching at this end, they may join together and get ejected out as H1 plus H2, that is H. Now during this, we can say 3K and 6K having same current H1. So the arrangement having same current must be called series. Is it clear?
Yes, sir.
So just arrange these two rods in series combination and 2K is in parallel with that combination. And just try to simplify it. Okay. Just use the concept of since all rods are identical. So A1, A2, L1, L2 must be equal.
Okay, sir.
Ifra, you got any answer?
So doing.
Okay, okay.
So my answer is coming 3K.
Good. So final answer will be 3K. Okay, any doubt up to this part?
No, sir.
So this is all about the conduction part. We have just finished it. In next class, we'll start with radiation, the last part of this chapter. Okay.
Okay, sir.
Okay then.